Okay, so today we're going to talk about the moment of inertia, and specifically the moment of inertia of point masses. The moment of inertia is just another name for rotational inertia. So let's think about this. Inertia is an object's resistance that changes in a motion. So rotational motion is an object's resistance that changes in rotational motion. And moment of inertia is a property of an object about some rotation axis. So things with a higher moment of inertia are harder to get to start rotating or to stop rotating. So the equation we're going to look at now is the equation for point masses. So a point mass is some little object in space. So the symbol we use for moment inertia is I, and the equation is going to be the sum of all the little masses that are some distance from a pivot point. So we'll say I to 1 to n, however many there are. So if we were to write that out, it's just m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus and so on, where m is the mass and r is the distance of that mass to the rotation axis. And again, I is the moment of inertia. Great. So now let's go ahead and just write down the units for moment of inertia. Try it yourself, and then you can check this video. Okay, so moment of inertia, so units we'll oftentimes use, and again, there can be zillions of units, but something dealing with mass, something dealing with radius squared. For the SI units, oftentimes use mass in kilograms will oftentimes want, and the R will oftentimes want it in meters. Okay, so now we're going to go ahead and solve two problems involving moment of inertia. So for our first problem, we have a massless rod, and we have 2 point masses, a 5 kilogram and 5 kilogram, one 2 meters away from the pivot point, and one, it looks like 5 meters away from the pivot point. So first thing I'm going to do is I'm going to write down my equation for moment of inertia. So I know we're dealing with point masses. The rod is massless, so this rod, I don't even have to worry about it at all. So it's m1 r1 squared plus m2 r2 squared. We're only dealing with 2 point masses. So mass 1 is 5 kilograms. I'll call this M1 and I'll call this M2. Excuse me, that should be R1. And then it's 2 meters away from the pivot point squared plus M2 is 5. And it looks like that is a total of 5 meters away from the pivot point. Perfect. I go ahead and do a little math and I get 145. My units for mass are in kilograms and my units for mass is in meters. Great. So the cool thing about this, the more mass there is farther away, will that increase or decrease our moment of inertia? So we know that will increase our moment of inertia. One thing I oftentimes think of is like tightrope walkers, they'll sometimes have like a long rod that they use in their hand that is more massive at the end. And that is just going to increase their moment of inertia, so their resistance to changes in motion, and make it easier for them to balance. Go ahead and try it yourself. Great. Okay, so we have one more example problem that we're going to go through together. First, I encourage you to read this problem, try it yourself, and then you can check back in on the video. Okay, so in this problem, we have small blocks, each with mass m, so I'll go ahead and draw that out. So small blocks, each of mass m, are clamped at the ends of a light rod of length L. So light rod, that's kind of synonymous to massless rod, so we don't care about the inertia of the rod. Great, so here's this. The length of the rod is L. Great. Compute the moment of inertia of the system about an axis perpendicular to the rod and passing through a point 1/4 of the end, 1/4 of the length from one end. Okay, so let me draw that. So this is going to be 1/4 L. Okay, great. And again, it tells us you can ignore the moment of inertia of the light rod. Oftentimes, light rod, massless rod, those will be synonymous to ignoring the the inertia of the rod. Great, so that's 1/4 L. So this length right here, just to label it, is going to be 3/4 L. Cool. So again, this is another problem with point masses. So I is going to be m1r1 squared plus m2 r2 squared. Cool. So for mass 1, that's just m. R1 is just 1/4 L. M2 is m. And then R2 is 3/4 L. And again, R is always the distance to pivot point. I forgot to square that there. Great. So this is m 1/4 L is going to be 1/16 L squared plus this is m times, that's 9 L squared over 16. Great. Just to make this easier on myself, I like to put the fractions out front. ml squared plus 9/16 ml squared. So that is what? 10/16 ml squared, which will simplify to 5/8 ml squared.